Okay, thanks a lot for the invitation. My name is Matías Martínez. I work in the University of Hauts-de-France. That's quite near from here, from Belgium. And I will present a collaboration. Yes. So, I will present a collaboration that we have done with Martin Montperouse. Maybe you know Martin Montperouse. He's working on automatic software repair as me. He was working with me at the University of Lille. So today the goal is to present Astor. Astor is a library or a framework for building automatic software repair approaches. Okay. So the goal of this talk is to introduce automatic software repair and also present Astor. So what is Astor? Astor is a framework for building automatic software repair approaches. Actually, it provides some routines that developer can reduce, and also provides the implementation of 5 repair approaches that are already implemented and are already ready for use. So, how can we use Astor? So, Astor was used up to now for, let's say, the world of academical work, researchers from different universities that they use Astor for creating new repair approaches or for extending those that are already provided. But also was used for some software practitioners which use Astor, for instance, for creating software boots. One of those examples is Repanator. Is here the reference that was created for Simon Surley, that was here in FOSDEM, so you can discuss with him. That was a software boot that proposed pull request with bug fixes. So the agenda for today is to introduce automatic software repair, the domain, then to introduce Astor, the extensions that can be done, and some experiments. So, what is automatic software repair? So basically, so imagine that we have a program that is here I call P that has a bug. So the idea is to take our approach. Let's say right now approach. I will not mention details of what is this approach. That takes a specification of the program, the specification of P. Also, we can call it coordinates oracle. And the idea is to create a version P that its behavior is acceptable with respect with the specification or with the oracle coordinates oracle. Additionally, this approach can consume, in addition to the source code and the specification, some artifacts, for instance, bug reports, traces, etc. So in this call, I will discuss, or I will mention 2 kinds of approaches for automatic software repair. The first of them are the test suite repair approaches, that they use test cases as oracle, as a specification. So what is the idea? Imagine that we have the program P. The specification will be the test case. So that means that we have one failing test case. That means that the program is buggy. Okay. However, if we have all the test cases that pass, that means that the program is okay, it's valid. It's valid with respect with the specification. That means with respect with the test cases. So that's the idea. So the idea of this approach is to turn the behavior to change the behavior of the program with the goal of passing all the test cases. Okay? So, and the second family of repair approach that I will mention today is the family of generate and validate approach. So the idea is to generate a candidate patch, to validate, and to see the result. That means in this case whether it passed all the test cases. If the result is not success, so it generates another patch until it finds a candidate patch that passes all the test cases. So there were present a lot of approaches from this family, test suite-based repair approaches during the last 10 years. But the problem was that those approaches was present in academia. So, and the prototypes, the code source, were not always available. Or in some cases, they were available, but for given languages. Okay? So our idea was to create a platform for Java. That means written in Java and for repair Java code. Our idea was to implement the state-of-the-art repair approach and also to provide some extension points to create new repair approaches. So we create Astor. That the name came from automatic software transformation for repair. Okay, Astor is available in GitHub. It's quite easy to use. So basically, here I put an example of the command. Here we have an argument that is mode, and here we specify the name of the repair approach that we want to execute. For instance, here we present three: Shake and Proc, Shake Kali, and Shake Mute. I will explain, I will do a small summary of them after, sorry. Then we say, okay, mode, here the repair approach that we want to run, the location of the application that we want to repair, where is the source code, the dependencies of this project that we want to repair, and the output. So, which are the repair approaches that we have implemented? So the first one is ShameProc, which is one of the most cited paper in the field of automatic software repair. The idea is that ShameProcs create patches by inserting, replacing, and remove statements. It works at a level of statements. Then another repair approach that we have implemented is ShameMute repair. It's a very simple approach that basically it mutates operators. For instance, from A greater than B, it mutates to A greater and equals to B. Very easy, very simple repair operators. And Shake Kali, that the goal is to remove code. Okay, remove statements, it adds return statement, replace if expression, etc. This is a summary of some of the approaches that we have implemented and are already included in Astor. We have developed also new repair approaches, for instance, Cardument, that here the goal is to replace expressions that by mining templates that we create by analyzing the source code are creating new instances. And the repair, there is an extension of Astor, for ShameProc, sorry, that use similarity of code for creating new patches. So here you have the URL to clone Astor. Here one example, as I mentioned before, the mode, the location, the dependencies. You can also specify the failing test case. We need at least one failing test case. The idea of Astor is to transform the behavior of the program with the goal of that this failing test case pass, but also it tries to keep the behavior that is correct. That means the test cases that are not failing, that continues passing all the test cases. And there are a lot of arguments, for instance, max time, that is the time that we give Astor to find, to search a solution. Okay. So, what is the output? We provide three outputs. The first one, the standard output, that shows here a lot of information. For instance, here is one identifier of the solution and the patch. Then we provide an output in JSON format, okay, the same information. And also in the file system, we write the patched format, the patched version of the program, of the file that was modifier, and the patch that you can apply them into your program. So, how does it work? So, the inputs of Astor are the Buggy program and the Oracle. The Oracle, in this case, are the test cases. So, the first thing that Astor does is to compute the suspicionist of components. That means that for each statement of the program, it computes or it puts the probability that this statement has a failure. Okay? It's a number from 0 to 1. And it computes the probability by running the test cases and measuring whether how many of them, how many of failing test cases cover the line. Then it creates a program representation. That means here we call to program variant a modification point. We'll see later. So while a given amount of time, it selects one suspicious line, okay? We call it modification point. Then we select an operator. We apply the repair operator to the statement to generate a patch. And then we validate the patch. That means to execute all the test cases. So after we end this loop, if we find some solutions, we sort the solutions according to some criteria. So every step can be customized. That means that we can override the behavior, the default behavior of one repair approach. So this is the list of extension points. You can see that here each extension point can be executed in one step of the workflow. For instance, here the default localization, we can plug in a new implementation of the default localization. Here in the program representation, we can say, okay, instead of working at the level of statements, we can work at the level of expressions. Then here we can say, okay, we have these new repair operators. So this is the list of extensions that we provide. For instance, for localization, we have 2 implementations. The list of operators that we provide, etc. So, how we use the extension points? So, it's quite easy. So, imagine that we have this extension point that is for localization. The for localization, what it does is to put the probability of suspicionist on each modification point, in each statement of the program. So the idea is we have an argument that is for localization, and here we put the value. We have 2 approaches for localization. One is Chase Salter, or the other is Coconut Spoon. We simply choose the value. But what happens if you want to create a new for localization approach? So imagine that we create a new for localization approach. That new code must implement an interface that we provide, and then we pass the name of the class that implements this interface that we have. So in the documentation of Astor, we provide for each modification point, which is the argument to use in the command line, and the interface to implement, or the Astor class that should be implemented for each modification point. Okay. How time do you have? Okay, thanks. So, I will detail 3 modification points. One is the granularity of modification points. So, the modification points are all the places that a repair approach, let's say all the places that the repair approach can modify. Okay. imagine that we have this code that has a bug. There are some approaches that work at the level of statements. That means that each modification point will be one statement. Okay? Then the repair approach will transform each modification point. That means, in the case of statement, you will replace, remove, or add another statement. That means that the granularity of that works a repair approach is a statement. However, we can change this granularity to work at the finer grain level. For instance, to work at the level of expression. That means that in this case, modification points are expression. That means that instead of replacing one statement, we can work and replace a particular expression. For instance, in this case, this method invocation, that is an expression, or this operator. So, see another example that say, okay, instead of working at the level of expression, we want to work at the level of Boolean expression. Okay, we want to modify only expression which evaluation is Boolean. So that means that with this extension point, we can work, or we can choose which granularity we want to work. That means to which granularity we want to generate a patch. Here we provide 3 or 4 different implementations, but you can create more. So then, once that we have choose the granularity, that Astor does is to create from the program under repair the DST. We use Spoon for that. Then we compute the suspiciousness of each line. So actually, the implementation of for localization that we use work at the level of lines. So they put for each line of the code the suspiciousness values. Then we say, okay, given an AST, we are interested of only some subset of AST nodes. Okay, that is according with the granularity of the modification point that we want. Imagine that we want to work at the level of statements, we only choose the nodes that are statements. Or if we want to work at the level of Boolean expression, we only choose the nodes that are Boolean expressions. And then we create the modification point by combining the information from granularity and suspiciousness. So finally, once that we have all the modification points, we need the repair operators. That means the operator that we will apply on each location. So for that, Astor has an extension point to say, okay, which are the operators that we provide. We can reduce the operator that we have already implemented, or we can create new ones. So here also we have an argument that is operator space, that we can put the value of the operators. In this case, suppression means all the operators that removes code. But also we can create new operators by, here we have the interface, or sorry, the Astor class, with some methods. One of them is, can be applied to points. It receives a modification point, that means, for instance, a statement, and return true or false whether this operator can be applied to this point. And another method that must be implemented by an operator is, given a modification point, to create an instance, or a list of operator instance. That means a list with possible changes that can be done in this point. Here the same, if we have new operators in new classes, we can pass in the repair operator argument. Okay, finally we have some extension points that are related with ingredients. So in that case, for instance, here, ingredient pool definition, selection of ingredients. So what is ingredient in this context? So Astor has two kind of operators. One is what we call autonomous operator that are used, for instance, for chain mutation repair. There are operators that don't need any information, okay? Imagine that this if. So we can apply a mutation in this operator, in the operator greater, and we have here different candidates. However, we have another category that is ingredient-based operator. That means that this operator, to synthesize the patch, need some information. This information can be another piece of code, a template, whatever. For instance, SessionPro has two ingredient-based operators, add and replace. That means, imagine that we have a statement and we want to replace one statement. We need another statement to be the replacement. So, imagine this case that we have this suspicious statement, this assignment, and we have an operator that from SessionPro that say add a new statement after this suspicious. So here the question is, okay, what statement we should add? So Astor has an ingredient pool which has all the candidate statement that can be inserted here. Then it will select one, let's say random, let's say return M, and create the new patch. So this extension point allows to create different strategies for creating the ingredient pool. So that means to creating this database of possible ingredients, possible that we will use to create the patch, for selecting one of them, and for transforming this ingredient, for instance, to replace the variables that are not of the scope. Here we have implement for these extension points strategies that are materialized in the deep repair approach. Basically, here we have implement one strategy to select ingredients according to the similarity, and another strategy for adapt an ingredient that has variables out of the scope according to the semantic meaning of the identifiers. So we have done several evaluations of Astor, or the approach that are built of Astor. One of them was it's based on one dataset of bugs that the name is defect for shape, that has different open source approaches. Bugs. Imagine that here each bug, so for instance for common langs, the dataset has 65 bugs, and on average they have 2,000 test cases. That means that there are large applications. And here our approach repair, for instance in this experiment, repair 33 bugs out of 224. That means a 14%. 14%, sorry. That means that this repair, this patch that we are able to generate, produce that all the test cases pass. Okay, but it doesn't mean that the repair are correct. Why? Because there are some changes that produce that all the failing test case pass, but are not correct. And why they are not correct? Because the specification is weak. That means that it's missing some inputs for validate the candidate patch. So the thing that we are working right now is to try to create new test cases to have more test cases for validating our patches. So, conclusions. So, I have presented a repair framework for repair Java code, and it's implemented in Java. Includes 3 repairs algorithms that were presented by the research community. We also provide some extension points for creating new approaches. So the source code is available, so if you have any questions or bug fix or improvement or collaborations, don't hesitate to contact us. Okay? Okay, thanks a lot. Do you have any questions?
Okay, so we have time for some questions. So perfect. Okay, so you go first.
So, as I understand, this is kind of a static analysis tool, right? You feed it, you train it with your code base, and
Yes.
with other source code, and then it performs an analysis which is total offline.
Repeat
Yes.
the question, please.
So, the question that your name?
This is actually preamble. So, if it is offline, how about using the fact that test case run, you instrumented some lines of code,
Yes.
to burn out the lines of code which may be a good candidate for substitution?
Yes, actually, yes. So, his question is that our approach is offline, correct me. Then we instrument the code, okay? We run all the test cases, okay, that we have, all the instrumented program, and using this information, we compute the suspiciousness of each line of the program. That is based on the coverage of the test cases. And based on this information of suspiciousness, we compute some, let's say, suspiciousness metrics to know, to have an order of the list of suspiciousness. And then we apply repair operators over these suspiciousness statements. Yes? So which function?
Speed of patching.
Okay, so his question is about the speed of patching. So the time that the approaches take to find a patch. So it will depend on the search space of the program. For some patches, the search space is quite small because the suspiciousness subspace is small. So for that, it will take some minutes. For others, it takes around hours. So, actually, we run the experiments for 2, 3, 4 hours, no more than that.
One last question on there.
It's all about the Java world. Is there a chance that you can also apply your results to C++ or
No. So the question is if we have applied the question in C++.
how much you can transfer that stuff to this other
We haven't we haven't tried with another programming language. So to repair another programming language. But for instance, for the approach that we have implemented ShapeProc, the original implementation is for repairing C code. So that means that this approach is already implemented in C code.
Okay, so if there's no more questions, thank you, Matthias.
Thanks.